Imagine a robot, right? One that can do anything. Not just a single repetitive task in a perfect factory setting, but one that can adapt to, say, your messy living room, find your keys, maybe even tidy up your desk a bit. That's the incredible promise of what researchers call generalist robots. Machines designed to tackle, well, a whole bunch of different tasks in all sorts of unpredictable, real-world places. The progress in AI and robotics here has been, honestly, breathtaking. But there's a catch, a big one. As these robots get more and more versatile, how on earth do you actually measure and compare how good they are? It's trickier than it sounds. So today we're doing a deep dive into a really groundbreaking research paper. It's titled RoboArena, Distributed Real-World Evaluation of Generalist Robot Policies. Our mission basically is to unpack how this new approach works, why it's potentially a huge game changer for AI development, and what it tells us about where intelligent robots might be heading. Get ready for some pretty surprising insights, I think, and maybe a whole new way of looking at robot performance. Okay, so let's unpack this idea of generalist robots a bit more.
We're talking about machines that go way beyond the factory floor. We're thinking about systems that can do complex manipulation, like opening drawers, carefully picking up delicate things, all in real places that are, let's face it, rarely neat and tidy. They're built for versatility. But this very flexibility, this adaptability, it actually creates a massive headache when you're trying to measure how capable they really are.
It's a huge bottleneck, yeah. Conventional ways of evaluating robots have always relied heavily on standardization, fixed tasks, very specific controlled environments, or maybe these big centralized robot challenges where everyone brings their machine to one spot. The core problem is that these methods just don't scale. They can't comprehensively evaluate these truly generalist policies across the huge range of tasks and environments they're designed for. Just think about it for a second. It's basically impossible to guarantee identical conditions every single time, like reproducing the exact scene layout, the same lighting, even accounting for tiny manufacturing differences between robots if you have a big fleet. You just can't copy-paste that perfect lab setup thousands of times in the real world.
So wait, the very thing that makes these robots so exciting, their amazing adaptability that also became their biggest weakness when it came to testing them with the old methods, that's quite the paradox.
It is, isn't it? But what's really fascinating here and what the RoboArena paper highlights is that this increasing generality, instead of just making the evaluation problem worse, actually creates an opportunity, a chance for a completely different approach. RoboArena basically proposes a paradigm shift. Instead of chasing this perhaps impossible goal of perfect standardization and centralization, it fully embraces decentralization.
Okay. So it's like a crowdsource thing. A distributed network of people or labs all testing robots in their own environments, doing their own tasks. Almost like a big global but somehow fair battle royale for robot algorithms. That sounds really disruptive. And I think I read that this approach was sort of inspired by similar things for language models like Chatbot Arena.
Precisely. Yeah, the inspiration comes from those successful crowdsourced benchmarks for LLMs and VLMs. And this decentralized design brings several key advantages, especially for generalist AI. First, it's open-ended. Evaluators can freely choose tasks and environments, which massively increases the diversity and realism of the testing conditions, way beyond what you could set up centrally. It's also robust. Because you have many different people or groups across the network contributing these double-blind evaluations, it makes it much harder for any single evaluator's biases or even just random errors to skew the overall results. Plus, it's inherently scalable. You can have dozens, potentially hundreds of evaluators asynchronously adding assessments whenever they can. And critically, it's adaptable. The tasks people choose can naturally evolve over time to match whatever the current cutting edge of robot abilities is. The benchmark stays relevant.
Okay, that sounds incredibly powerful in theory, but for you listening, how does this actually work day to day? What does an individual evaluator physically do with the robot to contribute to this?
Right. The actual protocol is quite smart, and it's really designed for fairness at that individual comparison level. An evaluator basically requests two policies, let's call them policy A and policy B, from a central server. Now, crucially, these are given out randomly, and the evaluator performs a double-blind comparison. They have no idea which algorithm is which. Policy A and B are just labels. Then, the evaluator sets up their own unique scene, whatever they want within reason, and they define a task using just natural language like pick up the red block and put it in the blue bowl. Then they run policy A, watch what happens, reset carefully, and run policy B, making sure the starting conditions for that specific A versus B comparison are matched as closely as possible. So while the tasks and scenes vary wildly across the whole network,
Each head-to-head fight is kept fair.
exactly, tightly controlled within that pair.
Okay, so the policies have had their go. How did the evaluators then feed back into the system? What kind of data are they actually recording?
They capture three main types of feedback. First, there's a continuous progress score, usually from 0 to 100. Just how far did the policy get towards finishing the task? Second, a simple binary pairwise preference. Did you prefer policy A or policy B overall? And third, and this is really interesting, a free-form text box where they explain why they preferred one or why they scored it the way they did. And this last part revealed something quite fascinating in the paper. They found that in about 11% of the comparisons, evaluators gave a clear preference for one policy, even when both policies achieved the exact same numerical progress score.
Really? Why?
Well, for reasons like one policy acting, quote, more swiftly or confidently, or maybe its motion seemed more natural or less hesitant. This captures a sort of feel for the performance, a nuance that raw numbers just miss. And RoboArena actually uses this preference data. It quantifies that feel to get a richer picture.
Wow, okay. So you've got all this diverse data scores, preferences, written explanations coming from all these different unique setups. That brings up a big question, though. If everyone's making up their own tasks and scenes, how on earth do you combine all that incredibly varied feedback into a single reliable ranking of the policies?
Yeah.
It sounds like comparing apples and oranges, potentially.
Yeah, that's a genuine challenge, absolutely. And RoboArena has a pretty clever mathematical solution for it. They take the traditional Bradley-Terry model, which is a standard algorithm used for ranking things based on pairwise comparisons, like in chess ratings or, well, chatbot arenas.
Right, I've heard of that.
Yeah. But standard Bradley-Terry assumes all comparisons happen under identical conditions, which, as you just pointed out, is definitely not true here. So RoboArena's version augments that model. It incorporates extra parameters to account for the variability. Things like task difficulty parameters. Some tasks are just harder than others. And marginal task probabilities. How likely is any given type of task to be chosen? And even policy task offsets. Maybe one policy is particularly good or bad at a specific kind of task. By adding these factors, the model can learn an accurate global ranking just from the preference data. The A is better than B votes, even with all that underlying diversity in tasks and environments. It learns not just who is better, but implicitly how much better and under what kinds of conditions.
That makes sense. And it's obviously not just about getting that final number one spot on a leaderboard, is it? For robotics research to actually move forward, scientists need to understand why a policy works well or why it fails. What are its strengths, its weaknesses, its common tripping points? That seems like the real gold here.
Exactly. That's absolutely crucial for guiding the next steps, especially when you're dealing with these complex AI systems. You need diagnostics. And RoboArena uses large language models, LLMs, and vision language models, VLMs, to automatically synthesize these qualitative insights from that huge pile of evaluation data. It gives a level of detailed analysis that would be, frankly, impossible for humans to do manually at that scale.
So there's like an automated pipeline using AI to analyze the performance of other AI.
That's pretty much it, yeah. A VLM, a vision language model, first looks at images from the start of the evaluation videos and the task description. It automatically categorizes the task like, is this a pick and place? Is it using a tool? And it describes the scene. Is it cluttered? What's the lighting like? Then an LLM takes all that, plus all the preference votes, the scores, and those free-form text explanations from the evaluators. And it generates a comprehensive policy report. It summarizes everything. It's almost like an AI assistant writing a detailed performance review for the robot policies. And it even cites specific evaluation episodes like see evaluation #123 for an example of this failure mode with links to the video evidence.
That's incredible.
It really is. And the paper showed this works surprisingly well. The VLM's task categorization was about 95% accurate, and the claims made in those automatically generated LLM reports like Policy X tends to outperform Policy Y on stacking tasks were actually backed up by the real win rate data. So it's generating genuinely useful evidence-based insights.
Okay, this decentralized vision, the automatic analysis, it sounds amazing on paper, but they had to actually build it, right? They needed a real-world test bed. What kind of robots were actually involved in this experiment to bring RoboArena to life?
Yeah, they built what they call the Droid RoboArena evaluation system, and it's based on the Droid robot platform. This setup typically involves a Frangipane robot arm, that's a pretty common research arm, known for being quite dexterous with 7 joints, allowing complex movements along with various cameras for vision. D-Roid was a good choice for several reasons. It is dexterous enough for lots of different manipulation tasks. It's relatively portable, so evaluators can reconfigure scenes quickly. It's also linked to a large open source data set, which helps. And really importantly for this distributed idea, D-Roid systems were already deployed across multiple different universities and research labs.
Ah, so the hardware base was already somewhat distributed.
Exactly. That was key. The whole system then has 4 main software parts. Servers hosted remotely to actually run the policy calculations, lightweight clients on the evaluator's end, a central database to store all the results, and a central server managing the whole process, like handing out the A/B comparisons.
Right. But getting a whole community of busy researchers in different labs to actually participate in something new like this, that sounds like a challenge in itself. How did they, incentivize people to contribute their time and robot resources? And maybe more importantly, how do they handle safety? You're letting external code run on potentially expensive physical robots.
Good points. They came up with a clever evaluation credit system. It's quite simple. For every pairwise evaluation an evaluator runs for the community pool, they earn 1 credit. They can then spend that credit to request an evaluation of one of their own policies against the others in the pool.
Ah, a quid pro quo.
Pretty much. It creates this mutually beneficial ecosystem. Everyone gets broader, more diverse evaluation data for their own work by contributing to the collective effort. And for safety, yeah, that was critical. They put multiple layers in place. First, any new policy submitted has to pass basic checks. Does it conform to the expected input-output format? Then it gets run in a kind of test environment first. A specially trained human evaluator is physically present, watching closely, ready to hit the emergency stop if the policy does anything unexpected or potentially dangerous. Only after a policy passes these safety checks is it actually added to the main pool for general community evaluation.
Okay, the system is built, people are incentivized, safety is considered. The moment of truth. When they actually ran this whole thing, what did the results show? Did RoboArena live up to the hype?
Well, the findings reported in the paper are pretty striking, actually. They really seem to validate the whole approach. RoboArena conducted what they claim is the most extensive real-world evaluation of generalist robot policies to date. We're talking 4,284 individual policy runs across dozens of different scenes, hundreds of unique task instructions, just a massive scale. And the paper demonstrates quite clearly that those conventional methods, the ones relying on standardization, they simply do not give you a reliable estimate of how well these generalist policies perform in the wild. That's a huge finding.
Wow.
In stark contrast, RoboArena's crowdsourced task-aware ranking method delivered significantly more accurate policy rankings. They measured this using Pearson correlation, basically. How well does the ranking match the underlying true performance? RoboArena achieved a correlation score of 0.98.
0.98, that's almost perfect correlation.
It's extremely high, yeah. Compare that to the conventional methods they tested, which only managed an R of 0.69.
So conventional methods are barely better than a random guess in some cases.
Well, 0.69 isn't random, but it shows a much weaker relationship to true performance. 0.98 suggests RoboArena's ranking is incredibly reliable and accurately reflects the relative capabilities of the policies, despite the evaluation diversity. The results also gave concrete insights, like showing that more expressive ways of representing robot actions consistently did better than simpler ones, and that certain methods, like discrete action tokenization, seem to outperform diffusion policies for tasks needing precise language understanding.
Okay, a 0.98 correlation is seriously impressive accuracy. But how fast can it get there? Does it need thousands and thousands of comparisons before the rankings become stable and useful?
That's another really interesting finding. RoboArena turns out to be remarkably sample efficient. The paper shows it converges to these high-quality, accurate rankings within just 100 pairwise comparisons.
Only 100.
Yeah, which is roughly the same speed, the same number of runs as conventional methods often use, but RoboArena delivers far more accurate and more diverse results for that same effort. So researchers can potentially get reliable feedback much, much faster, which could really speed up the whole development cycle for better robot AI. And if we tie this back to the bigger picture of robot capabilities, these extensive evaluations give some really valuable snapshots of where things stand right now with generalist policies. The strengths they observed? Well, current policies can operate pretty reliably across different camera views, different lighting, varied backgrounds. That's good progress. They're also getting increasingly decent at direct object manipulation. basic stuff like pick and place, pushing objects around, simple opening and closing tasks.
Okay, that sounds like solid progress on the fundamentals. But where are the big gaps? Where do these generalist robots still struggle when you ask them to do something more complex, something requiring more smarts?
Right, and this points directly to future work. The paper is quite clear about the common weaknesses. Policies often fall down on tasks involving tool use, using a screwdriver, a hook, anything like that. Cloth manipulation is another big one. So yeah, your dream of a robot perfectly folding your laundry is still firmly in the realm of science fiction, I'm afraid. Also, tasks needing precision alignment, think carefully inserting a key into a lock, or stacking objects delicately, those are still very challenging. And anything requiring complex, multi-step reasoning to figure out a sequence of actions for a more elaborate goal. The evaluations also shed light on differences between policy types. For instance, autoregressive policies, the ones that predict the next action step by step, tended to do better on pick and place and stacking, probably because they follow language instructions more precisely. Meanwhile, diffusion-based policies, which generate actions more fluidly, they excel at things like smooth sliding or wiping motions, but sometimes got tripped up by very specific instructions. And then there were simpler approaches, like binning policies, which just consistently underperformed almost everywhere. Often they just sit there, inactive or fail quickly. So it really highlights that while we're making strides, there's still a lot of work ahead to get truly reliable, truly general-purpose robot intelligence.
So stepping back then, what's the big takeaway here?
Yeah.
What does RoboArena mean for the future of AI and robotics research for the community?
I think its impact is potentially really significant, primarily as an open source, community-driven resource. It fundamentally democratizes this kind of large-scale, real-world robot evaluation. It means researchers, even those without direct access to expensive physical robots, can potentially train and evaluate their generalist policy ideas simply by contributing evaluation credits or submitting their policies to the system. That could seriously accelerate research towards more reliable, more generalizable robots. And in a field that's just exploding with new models and papers facing what some call information overload, RoboArena offers a vital tool. A clear, accurate, and accessible way to actually compare and understand how well different approaches are performing in the real world. It's a huge leap in how we benchmark progress.
What a journey we've taken through this paper. It really feels like RoboArena isn't just, another benchmark test. It's a whole new philosophy for how we evaluate complex AI systems, especially ones interacting with the messy physical world. By leaning into decentralization, embracing crowdsourcing, it offers a way forward that's scalable, incredibly accurate, and gives these deep qualitative insights. It's so much more valuable than just a score in a table in a report. But while RoboArena is clearly a massive step forward, the paper itself and just thinking about it raises some really fascinating questions for the next stage, doesn't it? Like, what happens when a measure becomes this effective? Does it risk becoming the target itself? People start teaching to the test, optimizing specifically for RoboArena in ways that might not reflect true general intelligence. That old problem, Goodhart's law. Or on the security side, how do you make sure a distributed system like this stays robust? What if someone tries to be an adversarial evaluator, deliberately feeding in bad data to skew the rankings?
These are the kinds of thorny challenges that are probably going to define the next chapter of AI development and how we measure it. Definitely plenty more to learn, but hopefully this deep dive gave you a solid head start.